Yeah.
I missed your Monday lecture, so is it basically the gist like, so all your lectures here can be uploaded to YouTube?
Yes. Yeah. Yeah. So the recording for Monday should already be up on the campus site. So if you just want to watch that, catch up. Mhm. All right, it's 5:30. It's going to get started. All right, good evening, everyone. How's everyone doing today? Good, doing good. Second half of the first week. And so, we're getting right into it. Okay, so today is our first lecture day, I guess you could say. So Monday, all we really did was we just went over the syllabus. And we just introduced the course a little bit. So today we're actually going to go over stuff. And so the goal for today is we're going to do just a little bit of review from heat transfer and fluids. You'd be surprised. There's actually not that much review that we're going to have to do before we jump right into it. But we are going to review something that maybe you might have forgotten from heat transfer, which is the heat equation. Okay. All right, so we'll go over that. We'll talk a little bit about what I call the discretization process, and so that's the process in which how we take a physical problem, a physical phenomenon, and then we'll turn it into a computational problem. Okay. And we'll explain just some general concepts of approximation, error, and convergence, which are going to be important whenever you do any kind of computational work, whether it's what we do in this class or if you're doing FEA or anything like that. Okay, and so announcements. I posted homework 1. So homework, the first homework is on Canvas. This is not the introduction email, so this is an actual problem set. And so if you take a look right now, most of that problem set is going to be programming practice, so MATLAB practice. And so, of course, if you feel confident in your MATLAB, you can go ahead and try to tackle it right now. But our MATLAB review will come next week. And so, I anticipate probably the majority of that homework assignment you probably won't be able to do it until after we review a lot of the MATLAB stuff next week. Okay, but you can take a look. You can get started if you want. You can probably answer some of the conceptual questions. But that homework, most of that stuff's gonna be next week. And so the due date for that is going to be not next Monday, but the Monday after that. So about 12 days from now. Okay. Right, and so that's all my announcements. Are there any questions I can answer before we get started for today? All right, let's go ahead and get started then. Okay. And so I like to call this lecture notes introduction to computational heat transfer. So we already kind of talked a bit about it on Monday, and so so a little bit from today is going to be a repeat, but I want to kind of repeat a lot of this stuff just to kind of just because they're important. Okay. All right. So let me start by saying that whenever you're doing any kind of engineering design or any kind of engineering analysis, kind of a very important part of that is to predict or to determine what's going to happen to a physical system when you subject it to external effects. Okay. All right, so I'm going to put emphasis on external there because, the way a lot of physical systems are, when they do any kind of interesting behavior, you can kind of look at it from a perspective of it's just kind of reacting to its external environment. Okay. And so let's take a simple case. And so let's say that you have frozen pizza that you want to heat up. Okay. And so the way that you heat up the pizza is that you put the pizza in your oven, you apply heat from the oven, and that cooks the pizza. Okay. And so one way that you can kind of interpret that is that you have a frozen pizza and it's reacting to the external effects of the heat that's coming from the oven. Okay. Another simple example, we have a stapler that's sitting on that desk. If I take that stapler, I throw it across the room, the stapler is going to go flying and probably break when it hits the wall, right? And so that stapler is reacting to the external effect of it being yeeted across the room. Okay. And so for this class in particular, we're interested in fluid and thermal systems, kind of with the more emphasis on thermal. Okay. And these situations are known to be particularly complex because thermal and fluid systems just naturally have very, very complex physics involved. Okay. But despite that, if you work, especially as a mechanical engineer, there are a lot of very common engineering systems that involve fluid and thermal physics. Okay, and so let's talk about some examples that you see kind of most often in engineering. Okay. So one, I'll mention this quite a bit in this class is HVAC. Okay? So if you don't know, HVAC stands for heating, ventilation, air conditioning. HVAC is really fascinating because it involves, a lot on several different levels. And so on the one hand, you have just the pure fluid side where you're moving air throughout an entire building usually. Okay? So as the air moves through, it's usually moving by some pressure differences or by some pump. And so there's a large fluid aspect to it. But a lot of times you're moving air through a building to control the temperature. And so you're either cooling the air, and that's air conditioning, or you're heating the air somehow, and that's heating. Okay. Two's pipe flow. So one of the more simple flows out there, but even then there's still a lot of complexity and a lot of nuance to how we can model and simulate pipe flow. Three is electronics. And so, when I mention electronics, what I mean is kind of the heating side of it, or I should say the cooling side. Okay. Whenever you have any kind of high power computer or high powered electronics, those often give off a lot of heat. And so, there's a lot of thermal engineering that goes into designing the fan or the cooling systems for these electronics. Ship design is another place where fluids plays a big role, of course, because the ship floats on top of water. And the fifth one I'll mention is aerospace. And so aerospace, there's tons of fluid and thermal applications everywhere. So there's kind of too many to talk about. Okay. All right. So this is just kind of a few of the application areas that maybe you guys are interested in learning more about, but a lot of what we learn in this class can be used to simulate these And in fact, a lot of computational methods are used in those lines of work. Okay. Okay, so let's talk about, we've talked about, how important it is for us to make predictions of these physical systems. We've given some examples of these physical systems. Now let's talk a bit about how we actually go about analyzing these systems in practice. Okay, and in particular, I want to talk about 3 different methods that we can classify engineering analysis into. Okay? All right, number 1. So number 1 is probably the method that you're most familiar with, at least through your other classes, and I call that analytical. So analytical, I like to call these, sometimes they're called pencil and paper methods. What these usually involve is you take the governing equations of whatever physical phenomenon that you're trying to model, and you solve them by hand, basically. Okay? It's like taking a test, right? So you take a test in like heat transfer, and the way you solve the problems is more likely than not going to be analytical. Okay? And so the benefit of analytical is that it's very fast. Okay, and so if it's a problem that you can solve by on paper, then that's usually pretty fast. Another nice thing about this method is that it's very inexpensive, okay? Because all it really takes is just a pencil and a paper, and so that's usually pretty cheap. But the downside to analytical is that because you're solving things by hand, we're really limited to how quickly the human brain can perform calculations, or in most cases how quickly you can punch numbers into a calculator, which you may think you're fast, but you're not faster than a computer. I guarantee you that. Okay. And so the limitation for analytical is that we can only really apply this to the simplest of problems. Okay. Which unfortunately is a big downside, because most of the times if you're doing any kind of engineering work, you want to work on something that is not so simple, right? So otherwise, it wouldn't be cool. And so I think analytical is a great, I would say, educational tool. And so that's why, we use it a lot in the classroom, because it's a good way to kind of illustrate core concepts. But for doing anything really practical, there's a lot of limitations of what you can do with analytical work. All right, number 2. All right, the second way that we could perform engineering analysis is what I call experimental. Okay. So with experimental analysis, basically you're not doing any math really involved, maybe afterwards in the post-processing. But what you're basically doing to say that there's an engineering system that I want to see how it physically is going to react. The best way to do it is to just try it out. Okay. There's no better computer, there's no better simulation than Mother Nature herself. Okay. If you want to know, if you want to learn, how big of a dent in the wall this stapler will make, the best way to do is just take the stapler and just chuck it at the wall, right? So there's no better way than that. The unfortunate thing is that for experiments, a lot of times they are pretty costly. If I put a dent in that wall, I guarantee you they're taking it out of my paycheck, which I definitely don't want to happen. Okay. And especially if you're doing any kind of destructive testing. And so any kind of destructive testing, you are destroying your test sample. Okay. And a lot of times, if you're setting up an experiment properly, it can be very time consuming as well. But the good thing about experiments is that no one really refutes your data. No one really questions, whether you did it properly or not, because it actually happened. So what I say is that experiments are always the best way to get kind of the best quality data. Okay. Okay. All right, so between analytical and experimental, we kind of have two methods on kind of two sides of the spectrum. So on the one side, we have a method that's very fast and very cheap, but you can only apply to simple problems. Okay. And on the other side, we have something that's often very costly, often very time consuming, but it can handle, basically almost any physical situation as long as it can, feasibly happen in reality. Okay. And so the one that, of course, we're going to be working with in this class is called computational. And so computational actually, it bears a lot of resemblance to the analytical method in that we are going to be doing math. And so we are going to be solving the governing equations. Okay. Okay. But the big difference here is that we're using computers to do the bulk of the calculations for us. Okay. And that's a big difference because computers are going to be a lot faster at solving these problems than any kind of human mind. And so the use of computers kind of gets around kind of the main drawback of analytical. Because given that you set up the problem correctly and in the right way, you can have a computer solve the equations for very, very complex situations that you wouldn't be able to do by hand. And so that seems great, right? So it seems like computation is kind of the best. It kind of gives us the best of both worlds, right? And so it's cheap, right? And so you don't need to destroy anything unless you're into just throwing your computer across the room. And it's usually pretty fast. And so even the most complex simulations can be run in a matter of hours most of the time. So what's the downside? So the downside for computational is that it often requires the development of a very lengthy, very complex code. And even if you have such a code, even if you have a tool, say like something like OpenFOAM or like ANSYS, it could still be very tricky to set up. It could be tricky to set up, and it could give you results that are wrong, but may not appear wrong at first. And so there's a very common saying that we have in computational sciences. We call it garbage in, garbage out. Okay? And so the thing about a code is that the code, a well-constructed code, I always say will never give you attitude. So the code will never criticize you, then will never make fun of the way you look or anything like that. The code won't tell you it's wrong. Okay. And so a code will often give you a wrong result and present it as if it's correct. Okay. And so what I mean by that is that if you use a computer code, like say you use ANSYS or say you use OpenFOAM or something like that, and you set up the problem just completely incorrectly, okay, you can feed that in. The code won't tell you that the problem is set up incorrectly. It'll just give you an answer, okay, and it'll present it as right. Okay, what this saying says that if you put garbage into a code, okay, if you put a wrong setup or a wrong way to set up the problem in, you're going to get something wrong out. Okay, and a lot of times it's not apparent when you're getting garbage out unless you kind of really know kind of the methods within it, and you really know how to use the tool. Okay. And so that's what we're going to focus on in this course. And so, we're going to be focusing completely on this last method here, kind of in all facets of it. And so, we will be working on the development. Okay. And so we'll be developing a lot of code in this course. And I think what you'll see is that, by developing a lot of these codes, you'll be able to better spot issues of when, you put garbage in, you get garbage out. Okay. All right, any questions on this? Okay. All right, so let's do a brief review of heat transfer. So, heat transfer is a prerequisite for this course. And so, we offer that only in the spring. So I think the majority of you probably have took it about a year ago. And so it's good to do a bit of review. But you'll be surprised that, we actually don't need to review too much from heat transfer. In fact, the only idea that I'm really going to bring up is something that is often talked about near the very beginning of the class, and that is the heat equation. So I love the heat equation. I think it's a very nice equation. It's not too complex, but it has a lot of very nice. It exhibits a lot of nice behavior. But I think what I like most of all for the heat equation is the name. Okay, there's no weird scientist name attached to this equation. The equation just tells you exactly what it's trying to find, which is heat. Okay, we call it the heat equation. So there's no weird Bernoulli or whatever attached to it. All right. So what is the heat equation? So the heat equation is a differential equation in its purest form, it's a partial differential equation. So when you solve the heat equation, what you obtain is a function that describes the temperature distribution within an object. Okay? Okay. Oftentimes, that temperature distribution is some function, right? In 2D, it would be t of x, y, but in 3 dimensions, we could do t of x, y, and z. But for now, we'll just focus on 2D. Okay? So as an example, let's say we have, some potato-looking object here. Okay. And if we solve the heat equation on this, what we obtain from it is some kind of function that tells us the temperature at every location within this object. Okay. All right. And so let's say the location for this point right here is maybe 1, 2. The function t of x and y. So if we do t of 1, 2, if we solve the heat equation, let's say that this is equal to 100 degrees C. Okay. Let's say at this point right here is location, I don't know, 10, 20. So if we plug that into the heat equation, maybe we get 65 degrees C. Okay. All right. So the idea behind a temperature distribution is that if you plug in the spatial coordinates of any point within an object, it should tell you the temperature. Okay. But what we're solving for is this t. So this t is our dependent variable. Okay. So I believe in for most heat transfer courses, at least I know the one that I taught last year, we focused mostly on just 1D. We talked about 2D a little bit, but there wasn't really much we could do, because solving PDEs by hand is a challenge. But that's not a challenge for computers. And so what I'm going to do is I'm going to show the full heat equation in 2 dimensions. And I will show you the unsteady version as well. Okay. And so what does this look like? And so we have the density rho. We have the thermal capacity C underscore P. First, we have a derivative of the temperature with respect to time, partial T, partial little t. Then we have these 2 terms, which probably you didn't go over in your heat transfer class, but we'll discuss what those terms are in a second. Then we have some second order derivative terms. And then we have an extra term there, Q dot. Okay. Is everyone familiar with this symbol right here? And so if you haven't seen that symbol before, all that means is basically it's a partial derivative. Okay. So normally you might have seen derivatives with the D. So this is just like cursive D. So it's just like a partial derivative. Put a box around this. And let's label all the terms in this equation. Okay. So let's start with big T. So big T is the temperature. Okay. We have rho, so rho is the density. We have K, K is the thermal conductivity. C underscore P is called the specific heat. And with the Q dot, what that represents is any kind of thermal production. And so we call that the source / the sink. Okay. So it's a big equation. So there's quite a lot going on here. Okay. All right, so clearly, an equation like this, a partial differential equation, this is normally very difficult to solve by hand. Okay? We do have classes on this, and so if you are taking 438, or if you're a grad student, if you're taking 538, you've probably gone over some methods to solve an equation like this. But for most cases, it's just not practical to go through the trouble of solving this equation by hand. Okay. All right. So what we're going to do, what we're going to be focusing on in this class is how do we write computer codes to solve this kind of equation right now. Okay. But before we do that, one thing I want to do today is I want to go through each of the terms of this equation and kind of talk about what they physically mean. Okay. Okay. Because when you see kind of a big differential equation like this, each of the terms in the equation, and by term I mean each mathematical unit there. Okay. Each term actually has a physical meaning of why that term is in this equation. Okay. So that point was said to me a lot when I was in college, but I think it didn't really dawn on me. I didn't really fully grasp it until I was in grad school. Okay. Because if you look at a big equation like this, it just honestly just looks like a bunch of random shit. Like, some scientists decided to put, a bunch of mathematical symbols together and say that's the heat equation, right? But in reality, each of these terms here has a very specific meaning and represents something that's actually physically happening whenever heat or energy moves from one place to another. Okay. And so whenever you come across like big equations like this in practice, or when you come across a big equation like this in a class, I think even more important than learning how to solve these equations is understanding what the physical intuition behind each of the terms mean. Because if you can at least understand that, you actually understand kind of a lot of what's going on in these kinds of systems. Okay, and so let's do the same thing for this. Okay, so there's four groups of terms here that I want to discuss. Okay, so let's start with this one. Let's we'll call this term one. So it's just kind of by itself. We'll ignore the constants. And so things like the density to specific heat, those aren't as important because they're not derivative terms. Okay, so term one. So term one, this is the only term with the time derivative. Okay, if you notice, all the other derivatives in the equation are space related, so they have x or y. But the only derivative with respect to time is this one. Okay, and so what this term is often called is this is often called the unsteady term. And so what this represents is the fact that heat or temperature or energy can change as a function of time. Okay? Right, even if you're standing in a fixed spot. So even if you're, let's go back to the pizza analogy. So you're sitting on, let's say you transform into a pepperoni, right? So you're pepperoni on a pizza sitting inside an oven, right? You're a pepperoni, so you can't move, right? But just by sitting inside that oven, that you're going to feel a lot hotter because the temperature is changing with time. Right. So one important subnote that I'll make about the unsteady term is that oftentimes we'll make an assumption called the steady state assumption. And so when we make the steady state assumption, this term is going to go to zero. Okay. And so the next group of terms that I want to talk about are these ones here. Okay, so it's both of the first order derivatives with respect to space. And so that's u partial t partial x and v partial t partial y. Okay. And so I'll mark that as group 2. And so these terms, group 2, are often called the convection terms. And so if you'll notice, in kind of the space where I define all the terms, I didn't define u and v yet, and that's on purpose. Okay. And so u and v here, what they represent are the fluid velocities. Okay. And so what the convection terms represent is that these represent the fact that whenever you have a flowing fluid, so you have air kind of circulating through a room, if you have water that's kind of flowing through a system, then that transport or that fluid can transport heat, can transport energy along with it. Okay. So let's define U and V now. So U represents the fluid velocity in the x direction. And V represents the fluid velocity in the y direction. So whenever you have a flowing fluid, that can transport things really, really easily, right? And so, going back to the pizza analogy, so let's say you're a pepperoni and you take the pepperoni and you put it in front of a really big fan, right? And so the fan is going to blow the pepperoni from one side of the room to the other, okay? And there you have kind of transport by convection. Okay? So heat is kind of the same thing. So energy can also be transported with the fluid, just the same as a pepperoni. Okay. Now we go to the next group of terms. And so these groups of terms I'll call 3. Okay. All right. And so if you need to look back at the equation here, the terms that I circled are all the second order derivative terms. And so those are the terms kind of on the right side of the equal sign. And they're second order derivatives with respect to x, second order derivatives with respect to y. Okay. All right, so these terms, they represent the same thing. And so what they represent is a phenomenon called diffusion. Okay. And so what these terms represent the fact is that even if there's no flowing fluid, right? And so let's say that you're in a room where the air is completely still, it's still possible for heat to move around in that room, okay? And so we call that passive spreading. So generally speaking, when you talk about diffusion, you're talking about movement of a quantity from basically high concentration to low concentration. Okay? And so in the terms of heat, what that means is that heat is going to flow from areas of high temperature to low temperature. Okay? So diffusion happens no matter if you have some kind of active fluid or any kind of active substance to kind of push it along with. Because generally, generally everyone likes balance in the world, and so in order to balance things out, things tend to go from high to low. Okay, so from hot stuff to cold stuff. And so the last term that is up here is this Q dot. So I'll mark that with a 4, okay? So let me go back up so you can see it. Okay. So I've kind of already labeled this term, and so this term has already been labeled as source or a sink. But let's talk about kind of what it means physically, okay? All right, so term number 4, so we call this the source term, sink term. Okay. And so these represent cases where heat or energy kind of like spontaneously get generated or spontaneously kind of appear within an environment. Okay. All right, so I use that term spontaneously generated, kind of I use it cautiously because we all know that there's a conservation of energy in the world, so there's no way for us to kind of just spontaneously generate energy. Okay, but oftentimes we convert energy from one form to another, right? And so let's say let's go back to the pizza oven because I'm really hungry right now. And so if you consider a pizza oven that's kind of sitting in the middle of your room, what that oven does is that it converts electrical power to thermal power. Okay. And so oftentimes when we're doing just a pure thermal analysis, we don't directly account from the electrical energy that may be coming from an outlet, right? And so if we were to do some kind of thermal modeling of a room, we would model that oven as something that's kind of spontaneously generating heat, even though we know, physically what's happening is that that oven is just converting electrical energy to thermal energy. Okay. It's just that, when we're solving this heat equation here, there's no term or there's no way for us to factor in electrical energy. Okay? And so when you have kind of a situation like that, where you're kind of converting one energy form to another, and it's not directly accounted for in your equation, you can kind of lump it in together with that last term. Okay. And so a lot of times what I think about that last term is that anytime you have any kind of weird or unique stuff going on, it kind of gets lumped into that term right there. Okay. That was kind of a long sequence. And so, I wanted to make sure I get through all of that before we kind of pause. So are there any questions on any of this before we move on? Yeah.
So if you remove the unsteady term, that's just the steady version of the heat equation.
Exactly, right. Yeah. And so for the first, I would say 4 or 5 weeks, we'll be working with the steady version. And so we're not going to bring that in. So actually the time derivative is handled differently than the space derivative. Okay. All right, so that's the heat equation. So that's everything you need to remember from 407. Okay. Probably this is something that you didn't expect because I think probably in most 407 courses, we don't go over the heat equation in this much detail, but kind of understanding the heat equation and what all the terms represent, that's going to be more important for this class, because what you'll see, probably starting at the end of next week, is that we're going to take this equation and we're going to convert it into basically a computer algorithm. And so when you do something like that, understanding what each term physically means is actually going to be really helpful as you develop your algorithm, and you'll kind of see why. Okay, so before I kind of move on to discretization, I do want to take a quick aside to fluid mechanics because I did kind of tease that a little bit. And so we have our heat equation here, and so let's write kind of the corresponding equation for fluids. And so the kind of the master equation for fluid mechanics is the Navier-Stokes equations. And so with the Navier-Stokes equations, this represents the conservation of momentum for a fluid in 2D. So I'm just going to write it really quickly. I just want to make kind of a quick point with this. And of course, this is only for one component. So this is just the X component of Navier-Stokes, and its momentum. Okay. So another very long and difficult equation. Okay. We just got done talking about the heat equation in detail. Okay. And so actually, if you look at this Navier-Stokes equation and you compare it to the heat equation up here, you'll see that there's actually quite a lot of similarities. And this is kind of the reason why thermal fluids kind of always gets lumped together in a lot of ways. Yeah. Oh, sorry. This one is a row, this one is a row, this one is a P. Right. Yeah. So thermal fluids, often get lumped together, and you'll see kind of very soon why, because the equations are actually very similar. Okay? So let me do this. So and I'll use the same colors here. Let's do that. Do that. We might not solve Navier-Stokes in this class, maybe at the very end. So I don't want to dwell on it too much, but I did kind of want to show you this cool connection, because I think not a lot of people realize this when you're seeing it kind of for the first time. Okay? So notice how I circled the terms here, and I gave it the same labels as before. Okay. So just like the heat equation, we have an unsteady term. So that's the term I circled in orange there. We have convection terms, so that's the terms that I circled in blue. We have diffusion terms, which are the terms I circled in purple. And we have a production term, which I put in quotes, which I circled in green. Okay. It's just for fluids, our production term is a little bit more specific. And so we use gravity for the production term. Okay. But you can see, if you compare the mathematical forms for each of these, it's a little bit hard for me to do because I'm scrolling up and down. They look very similar. So the unsteady term has just a single time derivative. The convection terms has a product between a velocity and a first order derivative. The diffusion terms are second order derivatives, and the source term is just kind of extra. Okay. So what you should see from this is that the heat equation and Navier-Stokes are actually very, very similar. Okay. So what this tells us is that fluid momentum. Oh, question. Sorry.
The term 3, is that a U?
It is a U. Yes.
Okay.
Yeah. Yeah. So the U here represents velocity. Sorry, it's hard for me. I should probably come up with a better. Maybe this is better. Yeah, and I can see this. If you're raising your hand and I don't see you, sometimes I kind of just get in the zone. So just yell at me. That's fine. Yeah, sorry about that. Okay. What was I? Yeah. So fluids and heat have a lot of the same similarities, okay? Which is really cool. I didn't realize this until I was in grad school. Unfortunately, the Navier-Stokes equation, even though it looks very similar to the heat equation, it's actually exponentially harder to solve. Right? It's like it feels so close, but yet it's still so far. So the reason is much, I won't kind of dwell on this because it's I can talk kind of endlessly about this, but there's kind of two main reasons why the Navier-Stokes are really hard to solve. Probably the biggest reason has to do with these terms, okay? And so even though the convection terms look very, very similar, they're actually very, very different than okay? So if you look at the heat equation, so this is not important information. This is just trivia, in case you're curious. If you look at the heat equation, we have a velocity multiplied by a temperature. So that's okay. That's fine. In Navier-Stokes, we have a velocity multiplied by a velocity derivative. And so that is what we call a nonlinear term. And so the thing about nonlinearity in engineering physics and in applied math is that nonlinearity really sucks. It's really hard to solve nonlinear equations. And so that's probably the main reason why Navier-Stokes is so difficult to solve. The other reason is actually this guy. So this one is actually not accounted for yet. And so this is our pressure term. And so pressure is something that's unique to fluids. Okay. And so the way we couple pressure with the velocities is also very, very difficult. And it presents a lot of difficulties when you're writing CFD codes as well. So actually a lot of attention when you're writing a CFD code, a lot of attention is paid to how you handle the pressure term, which is not trivial. And that's kind of what makes it really. Yep.
For the for term 2 and term 3,
yep.
Is it so partial derivative u, and that's the same for y as well?
Yes, correct. Yeah, so this is just the x component of velocity. And so there's another equation for this with the y. Yeah. So that's another reason is that for velocity for fluids you have x, y, and z components, whereas for temperature you only have just a y component. That's another reason why. Right. So why am I bringing this up? So why am I bringing up fluids if all I'm going to tell you is that it's really hard to solve? That kind of seems useless. The reason I'm bringing this up is that this kind of equation structure where we have unsteadiness, convection, diffusion, it's not just unique to heat and fluid. So there's actually more physical phenomena that follow this as well. Okay. So another physical phenomenon that actually follows the same structure is mass transport. So this equation right here, even though we started talking about it as the heat equation, it's actually very versatile. So actually, there's quite a lot of physical phenomena that actually follow this the same structure. And so for that reason, for this class, even though we call it computational heat transfer, you could very easily call it computational mass transfer too, or computational fluids transfer if you ignore the parts that are really, really hard. Okay. And so for that reason, I'm going to write the heat equation in a slightly different form, where it makes it kind of a little bit more general to all of these different phenomena. Okay. So I'm going to call it the general conservation equation. So this is the equation we'll mostly be working. It's basically the same as the heat equation. Just I'm going to switch the symbols around so that it's a little bit more general instead of talking just about temperature. Okay. Remove some of the constants as well, just to make it a little bit cleaner. So the biggest difference is here is that I've swapped out temperature for this kind of general symbol phi, okay? And I've removed a lot of the kind of the density and the specific heat just because, you know, they're not as important, okay? I do retain one constant here, and so I do have this constant lambda. Here is, I call it the diffusion constant. And phi, this is some kind of, I call it a conserved quantity. This could be temperature. So this is the main equation that we're going to be working with, you know, as we go through the class. All right, any questions on this? Okay, so we have about 15 minutes left in class today, a little bit less than that. And so last thing I want to go over today is what I call the discretization process. Okay, because what we have right here is we have, you know, even though I've kind of simplified this a little bit here, what we still have is a pretty complex partial differential equation, right? And so right now, as it is, you know, this is kind of impossible for us to solve, okay? But that's not the point of this class. We're not trying to solve this by hand. We want a computer to solve this for us. And so in order to get a computer to solve this for us, we have to get it to a certain form. So that's what I call the discretization process. So you can think of discretization as kind of the process that we go through to take a physical system governed by governing equations like this and transform it into a form that the computer can solve. Okay. But there's 4 steps to this process. So step 1 is to define the problem domain and the relative physics. Okay. So what this means is that, you know, if you're going to solve any problem, you first have to define basically what your subject is going to be or where you're going to solve the problem. And so it sounds, pretty straightforward, and it sounds pretty obvious, right? So if you're solving a problem, you have to define what the problem is. But this is the step, if you're going to make some assumptions. So if you're going to make some assumptions about your problem, this is where you make it. So a lot of times you can make some assumptions here to kind of simplify your problem in a pretty significant way. And ask some questions like, is your problem steady state? If so, then that obviously simplifies your equation quite a bit, so you don't have to worry about time derivatives. Okay. You might be able to ignore convection depending on what the problem is like. This step is also where you're going to define your boundary conditions. And so we'll talk about boundary conditions quite a bit over the next couple of weeks. But boundary conditions basically define any kind of external effects or any kind of external factors that are affecting your physical system. Okay. Step 2. Step 2 is to discretize the domain. Okay. And so oftentimes, if you're running a computational code, you're doing analysis on a geometry that's fairly complex. Okay. But the way that a lot of computational algorithms are designed, a lot of times they're designed to work not on complex geometries, but on very simple shapes. Okay. And that's okay. Because what we can do at this step is that we can take your complex geometry and break it up into a lot of simpler shapes. Okay. Another term for this step right here is we often call it meshing. Okay. So the idea with this is that, let's say that you have your geometry here. Okay. And so instead of solving the equations on a potato, you're going to take that potato and you're going to break it up into a lot of squares. Okay. So it might look something like this. Okay. Question? Yeah.
Essentially, like this discretizing the domain, sort of, like the mesh over it.
Exactly. Yeah. Exactly. So yeah. So the idea is exactly the same. So FEA and what we'll learn in this class are very similar in that they're both computational techniques, so that there's a lot of overlap. And so no matter if you're using finite elements or finite difference, which is the first thing we're going to over, or finite volumes, you're always going to have to do some kind of mesh. But I think what's interesting, especially for those of you coming from FEA from last semester, the way we're going to use the mesh is actually quite different. So, because I think in FEA we focused a lot on the shapes itself. For the first part of this class, we're actually going to be focusing on the points or the nodes, which is kind of a different way to kind of look at the mesh. And so another way that you can look at this is that instead of breaking up the geometry into shapes, we're putting a bunch of points or a bunch of nodes inside the domain, and we're kind of spacing them out equally, and then that's going to help us do our analysis. F3. All right, so step 3 is the one we're going to focus on a lot in this class because there's a lot of different ways that we can do this. Okay. And so step 3, I often call discretizing the equation. And so what this means is that, we're going to take our governing equation. So in this case, it's a partial differential equation, and we need to transform it into a form that's easier for the computer to solve. Okay. And it turns out that computers are really, really good at solving algebra problems. And so our goal for this step here is to take our differential equation or whatever our governing equation is and transform it into an algebra problem. As an example, so let's say that we have a second order derivative, okay? Next week, what we'll learn is that you can take a derivative term like this and then turn it into an algebraic expression. So instead of a derivative, we might have something like this. We might have t1 plus 2t2 t3 all divided by 2, or excuse me, delta x squared. Okay. And so instead of derivative, we replace it with kind of an algebraic fraction there. Okay. All right. So I don't want to say too much more on this because that's, we're going to spend the next few weeks on it, but that's kind of the bulk of this class. How do we take differential equations and transform them into algebraic? Right. And so step 4, very quickly, basically what's going to happen after step 3 is that you're going to get a very, very large algebra problem. And so what that means is that you're going to have a very large system of equations. And so you're going to have a lot of algebraic equations for a lot of unknowns. Okay. Oftentimes, we like to represent this system of equations in matrix form. So a matrix form for a system of equations often is AX is equal to B. Okay. It's a matrix, some big chungus of a matrix sometimes, and so this, for this class, we're often going to be working with things that are like 1,000 by 1,000. Okay, that's actually pretty small. Like that. And so what I always tell people coming to this class, you may think you're good at linear algebra until you're faced with a system of 1,000 equations and 1,000 unknowns. Then, you may not think you're very good at algebra anymore. But the good thing about this is that, at this point, you don't really have to do anything. Okay. This is actually the goal. And so basically our goal with computational techniques is to set up a system like this. Then we take the system, we give it to the computer, we say, do your thing, computer. Okay. You'd be like shocked and surprised because, a lot of times you run a system like this and you run a code like this, you end up with systems that are like, I kid you not, 1 billion equations and 1 billion unknowns. So the matrix is a billion by a billion, and a computer can handle that, and it's kind of incredible. We're not going to go up to a billion by billion, but just to kind of illustrate. All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all I had for today. I apologize. I think I might have missed some questions throughout the class because the screen was in the way. So, please yell at me if I ever do miss those questions again. I think from now on, I'll kind of move this screen to the side. But thank you guys for coming today. Next week, we'll start our MATLAB review. So, definitely, if you want to brush up on that beforehand, that would be great. I have homework 1 posted, so please take a look at that. But if not, hope you guys have a good weekend. So I posted the first homework, and so that one has, it's mostly going to be MATLAB practice problems. And so if you wanted to take a look and give it a try first, you can. But we're going to be going over that all next week. I just posted it first in case you wanted to look, people wanted to look first. But you can wait till next. Yeah. You guys have a good weekend.
Are we gonna learn about like different discretization schemes, like the different types?
Yep.
Of ways you can.
Oh yeah. So the first half of the class, we're focusing on finite difference, which I think is the easiest one to learn first, and then we're going to learn finite volume. Finite volume, I think, is a bit more industry standard. So I know OpenFOAM uses finite volumes. The one we're actually not going over is finite elements. So actually, finite elements is actually.
How's for FBA?
Yes.
You have to think.
Yeah. So actually, so I used to teach kind of the more like theoretical stuff in 410, but I kind of moved away from that because I think most people want to see answers.
Yeah.
And so I do more of the theoretical kind of code development for FEA in grad school now. So that's 541.
So then that means that the first half of the semester is kind of like generally more meshing than less than solving, I guess.
Actually, very little meshing. It's going to be actually step 3 right here. So actually, it's something that we haven't really done yet.
So it's just.
And so it's basically how to take an equation like this and put it in and transform it into a form that you can actually solve. Yeah. But that process, there are lots of different ways you can do that.
Yeah.
So FEA is one of them. Finite difference is one of them. Finite volume.
You go down a little bit.
Yes.
Just honestly, so it's 2 and 3.
Yeah. So meshing is step 2. So we're not really going to go over. We're going to work with pretty simple
okay.
geometry. Step 3 is more.
Oh, I see. Okay. Cool.
Yep.
See
Yeah. All right, Chris, any final questions before I wrap up the Zoom?
Only if you have a couple minutes after class.
Yeah, I do. I teach another class at 7, but I have a couple minutes now.
So our discussion yesterday,
Yeah.
it's 5:40 you were telling me about?
Yes.
Okay, and that's the class that's next.
Yes. Yeah, that's the one that's.
Is it going to be in this Zoom or is it going to be in a different Zoom?
It's in a different Zoom. I can give you that Zoom link right now if you're interested in.
Yeah. I went ahead and signed up for that one.
Okay. Okay.
I'm going to go ahead and take that option because
Okay.
although I do, before I finalize everything, probably should have a quick discussion with you about, because it's a graduate class versus the 400, 500, it's a 500 class versus the 400 class. And
right.
There's some, I just want to get some clarification on what that'll do for my, curriculum.
Oh, yeah. Yeah. So I think the policy is that you need to complete 30 units of graduate work, and and at least half of those need to be from 500 level courses. So,
right.
So that's
at some point there's going to be a cutoff though. Once you get that 15 units, they're going to say graduate, right?
Not necessarily. I mean, you can still continue to take courses, but before
Okay.
you can graduate, I think at least half of those courses need to be 500 level.
I had a conversation with Dr. Mayra Salav. I'm sorry, I can't pronounce his name.
Yeah, I know.
The graduate advisor.
Yeah.
I'm real dead set on taking 5 very specific classes, and I don't mind adding to that, but if adding to that makes it harder for me to take those 5 very specific classes, then I got to figure something out.
I see.
And those 5 very specific classes were in viscid fluids, viscous fluids, convective, conductive, and radiative heat transfer. So
I see. Oh, I mean, you can have more than half of your courses be 500 level. I think the concern is that you can't. I guess another way to say is you can't have more than half be 400 level courses, but you can
Right.
have more than half be 500 if that's your concern.
So what you're saying is I could have more than 30 units in general.
Yes.
Okay,
You can have all of them be 500 level if you really want.
Right.
I think you just can't have more than half be 400 level.
Right. Okay.
Yeah.
So I'm gonna take that. I'm gonna sit in on the 540 class tonight and
Okay.
make my final decision. I already enrolled in it, but I'll make that final decision sometime
Okay.
this
Okay.
week.
Yeah, sounds good. I think you can continue to be in course. I think the deadline to drop is February 6th, and so
Yeah,
you want to
it's like
stay in
1 or
kind of
2
both
weeks.
classes, right? So if you want to stay in both classes for now and kind of see how they're going,
Yeah.
maybe do the first homework assignments in both classes, and then you can kind of make your decision from there.
Okay.
Okay, yeah, I'll email you the Zoom link because I don't see a way to grab it from the Zoom right now. So you'll get an email from me very soon.
Okay.
Yeah.
I'll see you later.
Maybe
Go ahead.
let's see. Oh, the link is right here. Let me drop it in the chat. That's a bit easier.
Okay, I see it.
Okay, do you have a copy?
Yeah.
Okay,